So hi everyone. The webinar will be, as you know, will be split in like 4 categories or 4 sections. We're going to start with using Quark to integrate to the hardware, in particular the Servo-2 system. Second part, we'll be designing a position controller using a PID-based position controller for the servo motor. Then we're going to start delving into control design. So we'll be designing a state feedback controller for the pendulum in order to balance the inverted pendulum. And later on, we'll be implementing that controller. So all the controllers will be built from scratch. Yeah, so let's begin. So I have MATLAB already open here. And I'm just going to go to File, New, and open up a new Simulink model. So here's my Simulink model. So I understand most people are familiar with MATLAB Simulink, so I'm not going to go too much over the usability of MATLAB Simulink. But this will be more for, especially this section is a lot for people that don't know Quark, want to know what it is. This kind of gives you a good glimpse of that. So I want to integrate to my hardware. So what you see on the webcam is you see a couple of devices. So I want to talk to the servo system. I want to measure the angle of the servo, and later on I want to apply voltage to the servo. So I'm doing that through the amplifier. So this is a single channel voltage based amplifier that we manufacture called the Volpac X1. We have a 2-channel USB based data acquisition device called the Q2 USB. So I'm going to be acquiring data and applying voltages to the amplifier / motor through this DAC. And then we have the Servo-2 system, which is a servo system that we've had for a long time here at Quanser. It has 3 sensors. It has a potentiometer, a tachometer, and an encoder. We'll be using the encoder today to measure the angle, and then we'll be applying, like I said, voltage to the motor, which drives the gearbox and makes the gear move here. So having said that, I will open up the Simulink Library. So here's the Simulink Library browser. When you install Quark, you get the menu called Quark Targets. So if I expand Quark Targets, there's different menus here, different categories, advanced, continuous, devices, and stuff like that. For this webinar, at least for this section, we're just going to be dealing with data acquisition. So I want to talk to my Q2 USB. So I'm going to go to data acquisition. I'll expand this category, and I'll go to configuration. So this is kind of the first step. So if I go to Hill Initialize, so I'm going to drag and drop Hill Initialize. Hill Initialize, so first of all, Hill, just to avoid any confusion, in case there's anybody in the aerospace industry, for example, Hill means something different. So Hill hardware in the loop. In this case, for these purposes, Hill just means an optimized data acquisition card made for control. So made for reading something and applying something right away. So in this context, that's what Hill means. So Hill Initialize is basically how I configure my data acquisition device. Right now you'll see it's set to Q8. Q8 is a different type of board, so I need to change this because I'm using, again, a board called a Q2 USB. So I'm going to double click on here, and this will open up the configuration. Great, so board type, I'm going to change my board type to the Q2 USB. Here it is. Then I will click on OK. So you'll notice before I click on OK and apply the changes that there are channel configurations. So I can configure analog inputs, analog outputs, encoder inputs, and so forth if you're a more advanced user. But for now, these default settings are fine. So I'm going to click on OK. So great, my board is set. The next step is I want to read the encoder. So now if I go under the immediate I/O category, the immediate I/O category has all my I/O blocks. So there's a block called the Hill Read Encoder. So I'm going to drag that. So the Hill Read Encoder points to the Hill Initialize block. So you'll notice under here it says Hill 1, and the Hill Initialize block is called Hill 1. So the Hill Read Encoder points to this Hill Initialize in order to use the correct data acquisition device. The reason I'm mentioning this is if you had multiple DAC cards installed in your system, you would have multiple Hill initialized blocks, and you would have these all these I/O blocks would point to different Hill init subsystems. Okay, so I've dropped my I/O block, the Hill read encoder. The next thing is I want to read the encoder. So for now, I just want to read the raw counts. So in case you don't know, the encoder, the raw measurement is counts. So it's not a very practical measurement, but we'll change that later. But for now, let's just drop a numeric display in here. So I went to the sync category. So this is an ordinary Simulink block, just a display block that's usually used in Simulink. And I'll connect these guys together. So now I have my encoder channel number 0 is connected to my encoder on my servo, and I'm reading that inside the Simulink model. Now, the Simulink model by itself is, right now, it is configured for simulation, but I want to set it up for QUARC. And what I mean by that is, so QUARC, one of the main things it does is it generates C code from a Simulink diagram. So the Simulink diagram really is only to design your controller or to do your quote end quotes coding. Once you finalize your control design in Simulink, and you generate the code, then it's kind of standalone. So the easiest way to configure your Simulink diagram is to go to the QUARC menu, and you could go set default options. Once I select that, then it sets it for the target on my host PC, on my laptop, which is a Win64 machine. So this sets like the template makefiles and all that stuff in order to generate the correct code for QUARC. So QUARC has been optimized to run in real time on a Windows platform. Okay, so before I run that, I'm just going to save my model. So I'll save this as QUARC webinar, and I think we're all set. So to generate the code, I go back to my QUARC menu, and there's an item called build. So if I go to build, then you'll see that in the MATLAB command window, it will show some prompts of compiling code, and then at the end it says it downloaded the controller to the CPU. So I actually have a QUARC executable that got generated from my Simulink model that will run on my laptop. So next step is to run my controller. So I'm going to go back to the QUARC menu, and I'll click on Start. This will start running the code. So click on Start, and then I'm going to move the bar. And as you can see on my screen, the counts are changing. So if I'm moving it back and forth, I'm getting a measurement. So in 2 blocks, I was able to get a measurement. So it's fairly easy to interface to this kind of hardware. And then when you want to stop it, you can go to QUARC and stop, or you can just click on the stop button here. So now we've obtained a measurement from the encoder. However, as shown, this is just generating counts. I'm just measuring counts. It's not very useful because I want to measure my servo angle in something more practical like degrees. So to do that, I can do some simple sensor calibration. I'm just going to move this over here, go back to my Simulink Library browser. I'll drop in a gain. And I know my encoder, this type of encoder, in quadrature mode, it'll generate 4,096 counts for every revolution of the motor. So if I want to get that in degrees, then I just say 360 degrees divided by the total number of counts per revolution. That will give me my servo angle in degrees. And just to make sure, I'll validate that. So I'm going to save. I'm going to go back to QUARC. But faster, I can go to, instead of going QUARC build, I can just click on this icon. So I'll go to QUARC. I'll just build it through the icon on the Simulink toolbar. Okay, it's been downloaded. And then I can connect to the target. So instead of going QUARC start, I can go on the toolbar. I can go connect to target. This connects to the code, then start. So now let's rotate this half a revolution. So if I go half a revolution here, see I'm measuring 180. If I go the whole way, then it should give me 360. It is. So that's good. I've just validated it. If I go back, just to verify, I should get my 0 degree value. So this is important. You can even do this for teaching students how to interface the sensors. Like this is for someone just starting in interfacing the hardware. This is pretty huge. So simple sensor calibration and validation of the measurements, builds confidence. So now we know that we're measuring the right angle. I can stop my code, and the next step now is to apply voltage to the amplifier. So my DC motor is connected to the amplifier, is driven by the amplifier, and the amplifier is connected to analog output channel number 0 on my DAC. So I'm going to go back to the QUARC targets immediate I/O category, and there's a block called hill right analog. So if I drag and drop that inside my Simek diagram, then it's already set up for channel 0, so that's good. And I can then go to the ordinary Simulink library, go to sources, and I'll put a constant. Constant of 1 is fine. So I just want to apply 1 volt signal, nothing huge, just make sure that I can actuate the motor. So I'll save that, I'll go to build. Okay, it's done, and connect to target and start. Great. And stop. So that's good. So now I've managed to apply voltage to my motor. Now the other thing I want to make sure of is so now we're almost ready to do like a simple proportional control, but there's certain conventions we need to adhere to. So the first thing, one of the most important things, is if I apply a positive control signal, I want to make sure I'm getting a positive measurement. Otherwise, it'll go unstable. So in order to view this a bit more properly, I'm going to put a scope instead. So I'm going to put a scope. I'll call this Servo Angle in degrees. I'll save. So open this up. So this shows you that you can use different, again, I'm using inherent Simulink blocks. There's nothing, these are not extra blocks or anything like that. This is all blocks that you can reuse in Simulink. So if I run this and I do auto scale, I can, oh, see? So now it's, I'll do auto scale again. It's going from 0 down to -300. So I'm not actually adhering to the conventions that I want. So I need to change this. I need to do actuator calibration. So to do that, I'll just add a gain. I'll put a gain here. I'll set this to -1. Oh. -1. And this I'll just call motor convention. So I'll save that. Move this down a bit. I'll just adjust my scales to show full range. Okay, save, build. Okay, that's done. And I connect to the target and I run. Great. So now, applying a positive 1 volt signal, I'm getting a positive measurement. So that's good. That's good. So now we're ready for the second part of this, which is controlling the position of the motor. I'm just going to reset this back to the 0 angle. So let's just start with a simple proportional control. So the first thing we need is negative feedback. So I'm going to go inside math operations, the Simulink Library math operations, and I'll add a summer in here. So I'm going to double click on this, and I'll add the negative sign. Definitely don't want a positive sign on that. Delete the display. I won't be needing that any longer. So the measurement, or my process variable, goes to my negative terminal. Now on the positive terminal, I want my set point, so I want my desired angle. So for that, I have a whole choice. So I'll go to sources and Simulink sources category, and I got a few options here of what I can use. I usually I'm just going to take the signal generator block and I'll put a gain in there as well. So this will be my motor set point. So I'll connect these together. So I'd like to generate a square wave, and I'm just going to decrease the frequency to 0.4. And then this is all in degrees. So I want this to go plus or minus 30 degrees. So this should be going plus or minus 30 degrees once I get my proportional control. I will no longer be supplying a constant voltage. Now this is going to be replaced by a controller. So I'm just going to connect this here. So we know so you got to make sure you keep the motor convention here, otherwise it would go unstable. So that's why we did the check previously. And here, I'm just going to reduce the gain a bit, and I'm going to call this KP. So this is my proportional gain. So I have my set point, so square wave set point plus or minus 30 degrees at 0.4 hertz. I'm getting my angular measurement in degrees to my negative feedback terminal, being fed to a proportional controller, then applied to my motor. So let's build that and see how that goes. Okay, great. Connect to target, run. Great, so that looks like it's performing correctly. I'll go to my scope just to view. So that's not too bad. But typically I would rather have my set point signal displayed in parallel as well. So I want my measured and my reference signal both to be shown on the same scope. So I'm going to stop this and I'm going to go to the mux in here, and that way I can overlay two signals. So I'll just delete this and I'll add the set point signal and I'll add the measured signal and put this both in the scope. There you go. Save. We'll build that. Connect to target, run it. So now the yellow signal is my set point, while the purple is my measured. So I can adjust this. I'm gonna change my scales here, and then I'll change the axes to be about like that. So just change my scope settings a bit. So the proportional gain is kind of low. I'm getting a bit of steady state error, so I can increase it. So I don't need to stop quark. I can do this on the fly. So parameter changes are done in real time. So I'm going to increase this to 0.2. Okay, that's pretty good. Or 0.25. There. So that's a fairly fast response. I'll stop that. So that's a pretty good response, very typical second order response. However, I am getting some overshoot here because my proportional gain is quite large. So to remove this overshoot, one of the common ways is to add derivative control. So to do that, I need another gain. So I'll need a derivative gain. So I'm just going to expand this so you know what. So here's my proportional gain, and then I'll add a copy. Just copy that gain here and call this KD for derivative gain. Initially, I'll just set this to 0, and I'll slowly increment it when I run it. Now, I need to take the velocity measurement for this. So I need to take. So I'm just going to compute it. I'm just going to derive the velocity computationally in the Simulink diagram. So I could use a derivative, but that, especially for when you're measuring encoders, is prone to a lot of noise. So the best thing would be to have a derivative pass through a low-pass filter. Or if you just put those together, it's just a high-pass filter. So that's why I'm going to go to the continuous category. I'm going to go to transfer function. And then I'm going to set this to a high-pass filter with like a cutoff of 50 rads per second. So this will eliminate this will give me my velocity while keeping the noise down. There we go. So I'm just going to move this over a bit. I need more room. Okay, so this is your classic PD controller here. So I'm going to connect the error here, and then I'll add an add block. So I'll go back to math operations and add these two control signals together. Here we go. So we can save that. So all I've done here is just add the derivative control, and I just added that. So right now it's set to 0, but let's keep it to 0, and we'll just slowly increment it as I'm running it. That way you can actually see the effects of it as well. Minimize that, connect to the target, I'll run. Okay, so then if I increase this to, let's just keep a low value. So see, now we remove that overshoot. So just to show you again, I'll go back to 0. So I have no derivative action. This is my proportional controller where I get overshoot. And if I set this to a low gain like 0.005, then it gets damped. So there is a simple PD controller to control the position of our DC motor. So now we're ready for the third part, which is entering on model control with a state space design. And so for this, we'll be doing, for the third part, it doesn't actually involve QUARC. It's mostly only MATLAB and designing the actual gain to balance the inverted pendulum. So before we get into that, I'm just gonna disconnect this module. Okay, so now we're in part number 3, and this will delve more into MATLAB Simulink. So I have a couple of scripts that are already made in here. So they're called, I got 2 scripts, RoadPen, we got RoadPen parameters, and the inverted pendulum model, the state space representation. So RoadPen parameters are just a list of parameters for this system. So I'm going to run this to load all the parameters in MATLAB. And this was generated by us. I mean, this was generated from Maple actually, but there's different ways to do this. So, but this is a basic inverted pendulum model. So I'm going to run this as well and load that into my my MATLAB workspace. So what I want to do, I can do a bit of analysis now. So if I go to, so it loaded a state space system called RPSys, if you see this here. So I'm going to do a pole zero map of this just to look at the locations of the poles for this particular system. And as expected, it is unstable, as most of you know. So I have a pole on the right hand side, one on the 0. So it's an unstable system because we're dealing with the inverted pendulum. So that's fine. So I can close this now. Now the method I'll use for the state feedback, you can use pole placement, but I'll be using LQR for these purposes. So the default gains, so Q and R, for LQR, if you don't know, there's basically 2 weighting matrices, they're called. So those are kind of like the Q and R matrix, they're called. And the Q and R matrix, just very shortly, because I don't want to go too much into it, but you vary these Q and R matrices to generate a different control gain. So this, if you increase your Q or you decrease your R, then in general you have more control effort, you'll have a larger gain because the optimization algorithm will work harder to minimize the system. So, but this is all built in MATLAB, and so it makes it nice and easy to use these tools. So by default, usually Q is set to identity to start. So I'm going to set Q to just an identity matrix and R to 1. So those are my 2 parameters, and the rest is already given because the rest is my model. So I want my control gain to be saved under capital K and then I'll use the LQR command in MATLAB. The A and B state space matrix, I already showed you. This was loaded inside my script here. So this is what the script was used for. And then I say Q and R. So these Q and R again is what I'm tuning. Those are my guys. So then I click on that and it generates a gain. Now I'm not too sure if this gain is too high, too low. So I need to get an idea of that. So I've put together a very simple Simulink model that simulates the inverted pendulum. So I have a signal generator here that has a set point of plus or minus 30 degrees, just like we did with the DC motor. So that means that this will be moving plus or minus 30 degrees. I have the gain here, so the gain is set to K, which I just loaded using the LQR command. The Simulink block here is a state space Simulink block. This uses the whole model that I just loaded inside the system. So if I run that and look at the scopes, so I have Pendulum Angle and I have Servo Angle. So the Servo Angle shows me the yellow is my desired angle, whereas purple is my measured angle. And this is my Pendulum Angle. So it seems like the control effort is a little bit low, especially on the servo side. So in order to increase the gain that's placed on the servo, I need to adjust my Q and R matrices. R I'm just going to keep at 1, but Q I want to change. So I want my first element of Q. So if I go to diagonal matrix, so instead of saying it, I had it set to 1, 1, 1 previously. Now I'm going to set to 10 and keep the rest to 1. So now my Q becomes this. So my first element, 10, will put more effort on the servo angle, so I should get better performance. I go back to my LQR algorithm, K, generate new gain. So notice now my K, so this is my proportional gain that acts on my servo, this is my proportional gain that acts on my pendulum, and the rest here are basically derivative gains. This gain is different than the gain previously generated, because before I had -1, 22, -2, 3. Now, sorry about that, I have -3, 27. So all the gains are slightly increased. But again, it's an iterative process. So then I go back to my simulation, I run it. There, that's a bit better. Now I'm reaching my set point angle at the end of that cycle. I probably wouldn't be moving in this fast anyway, and in the actual implementation, I don't need a set point. So this is pretty good. It's a little bit more aggressive, and it should stabilize the pendulum better in this case. So let's try that. I think I'm okay with that. So this finalizes the third section, which is simulation only and control design. So just to recap, we designed a control gain using the LQR algorithm that is in the MATLAB control systems toolbox, and we validated that in simulation. So we're ready for implementation, at least the first trial. So I'll close this and I'll go back to my original diagram, which was used to control the motor. So now there's a couple of things that I need to do. Is the first thing would be to add the angle of the pendulum. So what I did here, just double click on Hill Read Encoder, and I'll add the encoder input number 1, which is where the pendulum is connected to. Click on OK. Okay, so now I have a second terminal here. Then I'll just drag and drop it. So the encoder on the pendulum is the same as the motor. So it also has 4096. Only in this case, I don't want to be using degrees. I want to be using radians. So instead of 360 degrees, I'm going to go 2 times pi divided by 4096. Same for the pendulum. There we go. Great. So this gives me the angles in radians. I'm just going to remove these here for now. Move that. So now I need to build my state. So it's a state of 4 elements. We need the position of the servo angle, the upright inverted pendulum angle, and the velocities of each of those. So that's what I'm going to build right now. So I'm going to go with my signal routing, and I'll add a mux. I'll set this to 4. So we have. So you can think of this as a vector if you wanted to. I'm just going to expand this a bit. So my servo angle is all set. I can connect this. My pendulum angle is. So this is the thing you have to be cautious about, because remember that my state space model defines the inverted pendulum. So in my implementation, I need to define my angle that I measure for my pendulum as being the upright vertical position. And by that I mean when it's up here, it should be measuring 0, because that's how my model is defined. That's where I use that model to design my control gain. So I need to make sure that my actual system represents, follows the conventions of my modeling. So in order to do that, I'll go to math operations, and I just need to add, I can add a bias block, for example, and I'll just set this to -pi, -180 degrees, and connect that. So I got position of servo, and I got the position of the pendulum connected. Again, these are just converting counts to radians for servo and for pendulum. I can servo angle and pendulum angle. Okay. Basically the same thing I showed you for the derivative control. So I don't need this or this anymore. Delete these blocks, but I will need this transfer function that I made for the derivative control. So if you remember, instead of using straight derivative, I use a high pass filter. I'm going to do the same thing to get the velocities of those states. So servo angle, and then I make a copy of this and connect the pendulum angle. So servo velocity, pendulum velocity, here's my state. And then my state would go to the negative feedback terminal right here. One more thing, I'm not going to feed any set point. I just want to do a straight balance controller. So I'm going to have a constant block in here. And I'm just going to expand this a bit. Remember, I'm dealing with states, so I have to deal with 4 elements all the time now. So my set point is a state. It's no longer a scalar value. And that's about it. So now, before I so I'm gonna add a constant block just temporarily. I'm gonna wire this to a 0 because I just want to make sure that I'm measuring everything correctly, just to validate that my my actual system behaves like my model. So I'm just going to move this here, and then I'll make a copy, and I'll add the pendulum angle is the one I'm mainly concerned with. I want to make sure my pendulum angle is accurate. So so there's 2 things. I want to make sure that it's defined as being 0 when it's vertically up, but also that it's positive when it's counterclockwise. So those are the 2 things I want to validate. So I'm going to save my model. I'm going to go to build. And then I'm going to validate that. So I'm going to minimize this. I'll run the code. Okay, so my pendulum angle right now, it's measuring in radians. It looks like it's doing okay. So I'm just gonna, I prefer viewing all my angles in degrees, just a personal preference. So I'm just gonna go with Simek extras transformation. There's a handy block called radians to degrees. I'm just gonna put those for display purposes. minimize that. So I'll go to build, just a quick change. All right. So remember, everything is in radians because my model is in radians. My control gain was generated based on a radian-based model, all that stuff. I'm just displaying it in degrees. Okay, so now I'm at pendulum angle. So I'm just going to expand just to show you what I mean. So right now it's probably measuring over here. It's at negative 180. So if I bring it up, then it goes to 0. That's what I want. So I want this, because this is how my model is defined. So it's 0 about the vertical position. Also, it's positive when I rotate it counterclockwise. So that's good. It follows all my conventions. Now I can start building my controller. I'm going to stop, delete this constant block, and I'm going to go back to my Simulink Library browser. Alright, so what do we need? So we got a negative feedback loop in here. We need another gain. So we need to apply the control gain. So the gain is in my MATLAB workspace. It's called K, as you remember. We simulated that, so it should be OK. So I'll call this feedback gain. Another thing as well is you got to make sure the multiplication is in matrix mode, because this is a 4-element multiplied by a 4-element vector. So if you put in matrix, then the output of this will be a scalar. So that's very important, otherwise you'll get an error. Okay, the last thing is I only want the controller to be applied when the pendulum is about the vertical area. So when it's like around, let's say, plus or minus 10 degrees, that's when I want the balance controller to be engaged. I don't want it to be engaged down here, otherwise it'll move back and forth really quickly. So to do that, I go to similar routing. I'll put a multi-port switch. There's other ways to do it, but so I just want 2 inputs. I'll go 0 based. So 0 based means, so I want my balance controller to be, when it's on, that'll be port number 1. Let's just define it that way. So balance control on is on port number 1, and when it's off, it'll be 0. So this is basically like just a conditional statement. So apply 0, and then apply balance controller when it abides by the certain, when it's within plus or minus 10 degrees of its vertical position. So we need to wire this first terminal now. So I'm going to go to math operations. First of all, I want the absolute value of the pendulum angle. So I'm using the pendulum angle in degrees, which is fine, right? So I'm measuring the upright vertical angle. Here's the absolute value. And then I will go to logic and bit operations category. There's a block called compare to constant. So I'm just going to drop that in, and I'll set this to 10. So if the absolute value of the pendulum angle, whether it's plus or minus, is below 10 degrees, then turn on the balance controller. So I hope that's clear enough. So this is my pendulum angle, my upright pendulum angle, less than 10 degrees. It'll set this port to 1, and I'll be using my balance controller, which I set in my MATLAB workspace. Save, and I'll build. Okay, it's downloaded, so now I can run it. Alright, so now if I bring it up, oh, it's actually, let me see here, so it's less than 10 degrees, oh, you know what, I know what it is. So here's what the thing is. So this is good. So I met the thing is really when I built my state. So when I built my state, I had it connected here. So this is how I had it connected basically before. So I had my high pass filters connected to the raw encoder counts. I didn't have. They're supposed to be connected right after the servo angle, right after the conversion from counts to angle. So that's the major issue. That's why it wasn't measuring properly. Well, that's why it wasn't controlling properly. Because in that case, then it gets you would get counts per second. You wouldn't get rads per second. So yeah, so I've changed that now. So I've connected the servo angle in radians and the pendulum angle in radians to my high pass filters, and those converted to radians per second. So that was probably that should be the issue. So now let's try this again. I'll rebuild it. Okay, and then I will start this. There. Okay, so a little hiccup, but yeah, it seems to work pretty well. And then I could add a set point to this if I wanted to. So I could set this to pi divided by 6, for example, and it would go to that set point. But again, this is a constant set point. Okay, well, sorry for that little mistake there, but I think sometimes it's better. And yeah, that concludes the entire portion of the tutorial. So I'm going to stop this, and that's it. So thanks a lot for your time, and I think I'll hand it back to Tim.